Hello students, here comes the final topic of trigonometry, the complex numbers. More precisely speaking, is the polar form of complex numbers. As the name suggests, this is partly a continuation of the previous topic, polar coordinate system. We just went through polar coordinate systems, so I do not think we need separate review for polar coordinate, but for complex number system, I think we do. So let's review that. What do you mean by a complex number system? Here we go. Complex number system is a set of numbers given by x plus yi form, where x and y are real numbers and I squared is -1. So whenever you do some algebra of complex numbers, just regard I as a character and x, y are real numbers so that you can add, subtract, multiply, and divide, and so on and so forth. And whenever I squared shows up, replace it with -1. And that's how we do complex number computation. We have done this many times already in college algebra or before that, as a matter of fact, so I don't think it is particularly necessary to talk about any more specifics there. Instead, let's cover some lingos here. X part is called the real part, y is called the imaginary part. If you have x plus yi, change the sign of the imaginary part. X minus yi is called a conjugate. Why is it so important? Well, it's coming. And if you have x plus yi, x squared plus square root of x squared plus y squared is called a modulus, or absolute value. Finally, here's a big deal. X plus yi corresponds to x comma y in coordinate plane. So, in other words, we can represent a complex number in a point in a coordinate plane x comma y through its real and imaginary part. Let's go ahead with a couple of exercises to make sure what we are doing. So here we go. Z equals to 2 plus I. Find out the absolute value and conjugate. And then, of course, we want to plot it. And here we go. Conjugate, simply change the sign of the imaginary part. So 2 minus I. Okay. How about the absolute value or the modulus? Just put that into the formula, x squared plus y squared. And then take the square root of that. We have square root of 3. Simple. The next example, well, pretty much the same thing. Change the sign of the imaginary part, and then we get the conjugate. And then the absolute value, it comes from square root of x squared plus y squared. Another one like that. And let's look at the plot. Here we go. Let me see. Let's minimize these so that we can see the pictures and the problems in the same viewing window. Okay, we just made it. The first one, 2 plus I, is located in 2 comma 1. There's a solid blue point there. And the second, 3/5 minus 4/5 I, there's a solid blue point in fourth quadrant, because in this case y-coordinate or the imaginary part is negative. And the third, -3 plus 2i, there's a point, solid blue point in -3 comma 2 in the second quadrant. Those three blue points correspond to the complex numbers 2 plus I, 3/5 minus 4/5 I, and -3 plus 2i respectively. And the complex conjugates are the red dots, the hollow red dots, which are symmetric with respect to the x-axis because we only change the sign of the y-coordinate value. So instead of 2 plus I, we have 2 minus I. So we have those hollowed red dot at 2 comma -1. And the other points are kind of like those two. That's what the conjugation does, flipping with respect to the x-axis. And of course, we saw how to visualize complex numbers in the complex plane. It's easy, just x comma y. Now let's talk a little bit about the properties of conjugates, and those are just routine exercises, so I'm not going to spend any class time proving this. If you take complex conjugate again, x plus yi becomes x minus yi, and then change the sign again, then we get x plus yi again, so we get the original one back. That's too simple. And then the next one, absolute value of the complex number and that of its complex conjugate is the same. Well, we're taking we're taking square root of x squared plus y squared, and we're taking squared, so whether this y squared part is either y squared or negative y squared doesn't make any difference. Consequently, the absolute value of the conjugate and the original must be the same. The third one is the most interesting. If you multiply complex conjugate, then we get the square of the absolute value. What do you mean by that? We're talking about this kind of computation. So if you FOIL it away, what do we get? X squared, that's the first, and then the outside, minus x times y times I, and then inside, x times y times I, and finally the last, y squared times I squared. Oops, mistyped it. I squared. Now, do you see the simplification? xyi minus xyi and positive xy cancel each other out. Gone. And then this I squared is equivalent to -1. Consequently, change the sign. So what do we get? We have x squared plus y squared. And what is absolute value of z? It's square root of that. Consequently, this should be equal to the square of the modulus of z. And this is useful because if you have a fraction computation, then that's what you'll have to do. Multiply the conjugate of denominator to both numerator and denominator so that the denominator becomes the real number, the modulus squared. We just proved it. And the others, I'll leave those as an exercise. Sum of conjugate of the sum is the same as sum of the conjugate. Difference, product, quotient, the same. Now, where do we use this one? Well, let's see. We have some exercises here, but this is not a college algebra course, so we're not going to spend too much time on it. Let's just breeze through the third example. We want to express it in x plus yi form so that we can plot it. How do you do that? What you're going to do is to multiply the conjugate of the denominator to both numerator and denominator. Let me just open up the answer here and just show you. 2 plus I is multiplied to both numerator and denominator. Let me expand the font. And I just highlighted it in red. And then what we get? The denominator is nothing more than the modulus, square of the modulus, excuse me. And as we calculate it, we have 4 plus 1, so that's going to be 5. How about the numerator? Numerator, you can simply FOIL it over, and then we end up with 2 plus 11i in this particular case. So we have it 2/5 plus 11/5 I. The key is to make the denominator a real number, a single real number, so that you can separate the real part plus imaginary part like that. Now that we have expressed z into x plus yi form, finding out its conjugate is easy. Simply change the sign of the imaginary part, 2/5 minus 11/5 i. And then by plugging everything into this absolute value formula, x squared plus y squared, and taking square root of everything, we end up with the modulus. The other problems can be done kind of similar fashion, like for example, in case of f, you'll have to realize the denominator of the first fraction and realize the denominator of the second fraction, get x plus yi form for both of them, and then subtract one from the other or add one from the other, kind of like those. It is time consuming, but nothing spectacular there. Well, the fundamental theorem of algebra, this is actually a fallout from the notebook I created for college algebra, so let's not worry too much about those. There goes the review of complex number system, and in the next video we are going to talk about polar form of complex numbers.